Hello everybody, this is Mr. Johnson and this is Algebra 1, continuing to talk about quadratic functions. And today we are going to tie two big ideas together with these notes. These are Q1D notes. Here we go. For question number 1, we're going to graph this quadratic. It's given in standard form, which is the form with A, B, and C, and so that's usually how we open up. Okay, so if we're looking at A is the first number that goes in front of the x squared. Since it's just a negative for this problem, right here, it's going to be -1. B is the number, the coefficient that comes with x, which is -6, and then C is the constant at the end, -8. So all these are negative. We'll see what that does. We've seen so far that A, B, and C, all these three numbers, they have no correlation to the movements in the graph. This graph, since A is -1, is going to open down. It is a reflection. That's about the only thing you can tell from A, B, and C. Now, we've talked about a little bit of a shortcut to find the x value of the vertex. That got rid of a lot of work. So if you recall, the x value of the vertex is -b/2a. I would encourage you to write that every single time until you get it memorized. You'll have nightmares of -b/2a. So all we have to do is take the b value and put it in. So for this question, it'll be a negative for the negative here. And then we are going to have a -6 for the b value right there. So a -6 is going to make a positive here in a second. But before we do that, let's go ahead and let's focus on the 2a. So 2 times a right up here, 2 times -1. Now, this is just two little problems, a top problem and a bottom problem. So we said a negative makes a positive. So we have +6. 2 times -1 is -2. So all we have left to do is take 6 divided by -2, and that is -3. Now that's the x value of the vertex. To find the actual vertex point, we need to take -3 and just substitute it back into our equation. So I'll change colors to red. We have negative. We have a blank space where we're going to put -3 here in a second. We're squaring that. We're subtracting 6 times our -3, and then -8. So in keeping with spirits, I will have -3 be blue. So we take and we follow the order of operations, PEMDAS, if you recall. Please excuse my dear Aunt Sally. Peter ate my dang applesauce, or whatever you want to say. So parentheses is first, and in parentheses we only have numbers, so we don't have to do anything there. Exponents is next, and we do have some exponents. -3 squared, right here. -3 squared is 9. And then we have to do the multiplying. That's next. So we put the negative in front. We're going to subtract. And then we got some multiplying here at the back half. 6 times -3. That's -18. So again, we're subtracting a negative. We're going to make a positive. We bring down the -8 right there. And now, since this is like adding, we have -9 plus 18. That's 9. 9 minus 8. 9 minus 8, that's just 1. So when we put this together to make the vertex, we have -3, 1, x, y. So when we're going to graph this, we've done all the work we really have to do. We're going to take -3, 1, and we're going to go up here. Start at the origin, go left 3, up 1. That's the really important vertex point. So now, looking back to where we open down. So we're going to come back to our vertex, and we are going to go over 1, down 1, following that pattern. Over 1, down 3. Over 1, down 5. Now you guys also know, not only do we have the 1, 3, 5, 7 odd number pattern, but we have the pattern where all these points get reflected across that, that axis of symmetry, right through the vertex right there. So we take these points and we just flip them across. If it's 2 away, it's 2 away. If it's 3 away, it's 3 away. You could also go ahead and go left 1, down 1, left 1, down 3, left 1, down 5, left 1, down 7, all the odds in that direction as well. So now we're going to go ahead and we're going to draw our curve through here. Remember, it's a U shape, not a V. Perfect. So let's go ahead and let's answer a couple of questions. Again, pause this video if I'm going too fast, or if you need a second to look at the graph and make sure you did it correctly as well. The zeros. Remember, the zeros, another way of saying that, that's the X-intercepts. So my x-intercepts, we'll go ahead and mark these with orange right here and right here. So those x-intercepts, or those zeros, are at -4, 0, and we have two of them, -2, 0. Our domain, we'll go ahead and switch back to black. Our domain is going to be all x values. Okay, you can choose anything to put in this quadratic function, and it will work. The range, however, the range is a little bit trickier because at some point we stop and we turn around. At 1, that's the highest we ever go. So for our range, our y's are going to be less than or equal to 1. You're never bigger than 1. Okay, that's the top of your arch here. So all the y values here, less than 1, less than 1, less than 1, and you continue downward. Now looking at these coefficients right up here in the equation, -1, -6, and -8, do those tell us anything about where this graph was moved? Did we move left 1, or did we move down 6, or down 8, or left 6, anything like that? Well, if you're looking at the picture, no. These numbers didn't tell us anything, okay? So A, B, and C don't tell us where the graph moves. The only thing that we can really get is from the A value. A only tells us if it opens up or down. Which is important, but not very useful sometimes. And the only other thing that we might be able to get is the C value. You'll notice this point right here, 0, -8. If we consider that point the y-intercept, if we consider that, and look at our C value, -8. And if you go back to the graphs from yesterday and the day before, you'll start to notice a pattern. This C value is where we cross the y-axis. And that's because what happens when you put 0 in up here? 0 squared minus 6 times 0 is all 0, blah, blah, blah. Subtract 8 from 0 and you get -8. So the C value tells us the y-intercept, but that's the only other important thing. So we can write that as well. The C value tells us the y-intercept. Those are the only things that A, B, and C can tell us. It's kind of stinky that it doesn't tell us any more. But we can find the vertex, and then we can plot the vertex, and then we know the pattern for the rest. So let's go ahead and let's jump to where we are going with this. You'll remember when we talked about square roots, we had movements, and it just made graphing things so easy. For example, with f of x equals the square root of x plus 7, and then subtracting 3 afterwards, that plus 7 right here on the inside, that moved us left and right because it's affecting the x values here. So that actually shifted us left 7. It was backwards. It was trying to be tricky. So that left 7 is on the inside, and then at the end we have a -3, and those are the up and down shifts, the vertical shifts. And a -3, that's easy. That's just down 3. And we could graph that if we know the pattern, and it's really simple. Really, really simple. It'd be nice if quadratics did that, and actually they do. We're going to see that here in a second. For the second example here, the negative in front, we would call that a reflection. Very similar to the reflections we've seen with A. The inside, -2, that's moving it right 2. And then the +9 here at the end, +9, that's up 9. And you could be more specific with these. You could say vertically shifted, horizontally shifted, anything like that. But let's just keep it simple because that's the basic idea. Where we're going is we're going to try to make quadratics that follow these rules. And the form that follows these rules for quadratics We call that vertex form. In fact, this up here with the square roots, that's also called vertex form because it tells you the vertex, where you start. So you'll notice with question number 2, I have f of x equals a negative. That negative is in front of all this other stuff. What do we think it does? Well, that negative is a reflection, just like above. So let's go ahead and let's write that in. It's a reflection. Now the plus 3, on the inside of the parentheses, on the inside of being squared, that plus 3 does a similar thing to the plus 7 or to the minus 2. And that moves us left or right. And since it's plus 3, that's technically moving us left 3. And we'll go with the last number, the number at the end. Okay, the plus 1, I bet you guessed it, does the same thing as the up and down from above. So this is up 1, and we actually saw that in notes earlier this year. So not only are we having a reflection, we're going left 3 and up 1. So we follow those directions, left 3, up 1, and we put our point. The reflection doesn't come till afterwards. Okay, so we found our new vertex, and now the reflection means we open down. So maybe that's a good note to put in here. Opens down. So our other points are going to be right 1, down 1, right 1, down 3, and right 1, down 1, 2, 3, 4, 5. Then we can reflect those. Left 1, down 1, left 1, down 3, left 1, down 5, right here. And drawing in our beautiful curve, maybe, looks something like the St. Louis Arch. So if you look, are there any relationships between the graph for question number 1? Okay, right here, negative x squared minus 6x minus 8. Okay, and any relationships between the graph we just did? Y equals negative x plus 3 squared plus 1. Well, if you look at both of these graphs, they are actually exactly the same. They started left 3, up 1, and this starts left 3, up 1 as well. That's where that green dot is. What? Can we have two different equations and get the exact same graph? You betcha. That's what's really cool about quadratics. They are the exact same picture. They are just different equations. So they are the same. So how can we get to this easy format? Well, I'm going to show you here with this next question. How can two different equations create the same graph? This really comes down to the definition of having something squared. Okay, remember the order of operations. Whoops. Please excuse my dear Aunt Sally, PEMDAS. And if we go ahead, we have to do the exponents first. This is x plus 3 squared. And if we are squaring it, it literally means x plus 3 times x plus 3. It's two of them. It's a carbon copy. It's boom, boom, two of them right next to each other. So if we take x plus 3 and x plus 3, we have to multiply that. And it's been a long time since we've seen anything like that. But we're going to multiply it by foiling it, okay? Or double distributing is what I would rather call it, but a lot of people know it as foiling. So when you FOIL this, you have to multiply your firsts, x times x. You're going to get x squared. That's what x times x is. After that, you have to do the outsides, which means the x and the 3. So x times 3 here is 3x. And you're adding that, okay, because they're both positive. They're both positive. You're adding. Then the I stands for the insides, and that's the 3 and the x here. So 3 times x is also 3x, but you would be adding. And then the last question, or sorry, the last part of foiling or double distributing is multiplying the last. So you have to make sure everything gets multiplied by everything. The x gets multiplied by everything afterwards. The 3 gets multiplied by everything afterwards. But 3 times 3 here is 9. So we're adding 9 since it's positive. So we have x squared plus 3x plus 3x plus 9. And if you're on top of your game, which hopefully you are, you'll notice, hey, 3x and 3x. These are like terms. So we can combine those. So we have x squared from above plus 3x and 3x, boop, boop, makes 6x. And then we just got 9 hanging out. Now this is starting to look a little bit more like ABC form. In fact, it is the standard form with A, B, and C. But there's always a catch. Look all the way back up here. Okay, we had a negative in front. We also had this pesky plus 1. So those have to go back down here. We can't just forget about them. We can't just say, hey, see ya. So where is this x squared plus 6x plus 9? This guy is from the x plus 3 squared part. So the x plus 3 squared part had a negative in front, right there, and it had a plus 1 behind it. This looks scary. Don't be terrified because all we have to do is distribute the negative. That's technically a negative 1, but I like to think of it as, hey, you're just going to make it touch everything inside, right there, and you're going to flip the sign. Okay, so this is going to become a negative x squared, and since this was plus 6x, now it's minus 6x. Since this was plus 9, now it's minus 9. Yeah. Now, do you touch the 1? No, because the 1 is not inside the parentheses. So we're going to go ahead and just keep that plus 1 around. All right, let me draw a little arrow over here. Moving over. We'll go green. If you are looking, not only did we have a pair of similar things up here with 3x and 3x, but down here we get another pair of similar terms. So minus 9 and plus 1. What do we get when we combine those? Well, positive 1 and negative 9 should make negative 8. So let's go ahead and let's write that all out. So we have negative x squared minus 6x. Those guys are just hanging out. There's nothing to combine there. X squared is different from x. And then the negative 9 and the positive 1 made negative 8. Now, let's look at what we were trying to do here on the left and what we would be trying to graph here on the right. So we started off here in vertex form, moving left 3, up 1, having a reflection, and we're traveling all the way down here after we expand it out, and we have A, B, C form, standard form. Now look at up here, bing, bing. If we look at the top equation and the bottom equation, they are the same. So if we expand the vertex form, which is the parenthesis form, we arrive at standard form. Standard form, which is the ABC form. So secretly, as we've been doing ABC form, we have been doing a very complicated version of vertex form, the parentheses form, the easy peasy direction form. So they are the same. I know that we've said there are 2 different ways to write them, but they can go back and forth, which is awesome. Super cool. So for question number 3, do these 2 equations create the same graph? This is a good question. We're going to figure out the graph on the left, and then we're going to figure out the graph on the right. So let's go ahead and let's just start off with the ABC, the standard form. My A, 1. There's nothing in front, so we can multiply by 1. My B, negative 2. And my C is a good old 4. So this is going to open up since A is positive. Let's find the x value of the vertex. X equals negative B over 2A. So negative 2 over 2 times 1. Hold on to your shorts. Negative 2 is 2. 2 times 1 is 2. 2 divided by 2 is a good old uno. Putting 1 back into the equation. I'm going to switch to green. We have 1 squared minus 2 times 1 plus 4. 1 squared is 1, minus 2 times 1 is 2, plus 4. 1 minus 2 is negative 1. Negative 1 plus 4 is 3. So my vertex, 1, comma, 3. Let's go ahead and let's graph that bad boy, going blue. 1, comma, 3. Right 1, up 1, 2, 3. Put that point there. We go back up here, opening up. All right. So we go over 1, over 1, up 3, over 1, up 5, out of room. Then we go left 1, up 1, left 1, up 3. And we can draw our curve. Whee! So it's a good old U. All right, here we go on the right-hand side. F of x equals x minus 1, that quantity squared, plus 4. So let's label our movements. Minus 1, that's moving us right 1. Plus 4 at the end, that's moving us up 4. So if we are traveling right 1, up 4, and my graph opens up, since there's no negative, so no negative in front, we go right 1, up 1, right 1, up 3, and left 1, up 1, left 1, up 3. That's as easy as that. Let's go ahead and let's real quick talk about zeros, domain, and range for this right-hand graph, since there was no work, basically. My zeros, if I'm looking at where I cross my x-axis, it didn't at all. If you were watching my cursor here, my graph never touches my cursor. I'm stuck here on the ground, and my graph is in the air. So for my zeros, we put the word none. For my domain and range, all x values, I can put anything in this quadratic, and it will work. And the range is higher than this low point here. So that low point occurs at 4. So my y values in my graph are all greater than or equal to 4. So the question that I was attempting to answer here, do these equations, this guy right here, and then this guy right here, do they make the same graph? Well, if you're comparing the left graph to the right graph, they look similar. But the right graph actually starts up here at 4. This one only starts at 3. So that means they are different. So these graphs, they're trying to deceive you. They're trying to trick you. These graphs are not the same. That is a good question. That concludes the end of our lesson here. And if you need to go back and pause the video because you didn't catch something or because you need to double check your work, I would encourage you to do that. Okay? So feel free. Go ahead, and you can always email me if you have questions. But I'd be happy to help you out. Okay? And I will be back to answer your questions at some point. So until that time, thank you guys and have a great day.